All right, so our second talk in this session is going to be by Sean Pichon and Kayvan Memarian. And so they're going to talk about an executable specification for a hypervisor. So please go ahead.
Okay, so the title is a bit of a mouthful, so maybe I'll start with a bit of history, or maybe a dramatization of history. So enter scene left Peter Sewell in the early 2000s, who looks at the state of the world and goes, well, surely by now programming language theory is sort of mature enough that we could try to apply it to real-world mainstream systems that people care about. We can try to verify some system software. And this is why, in your pocket right now, all the software is verified. So yeah, it wasn't, and they couldn't. Now we can try to look at why that happened. And in a sense, the theory was mature enough. And in 10 years, I have not done anything more complicated than a weak simulation, which had existed for ages at the time. But there were lots of other missing pieces. And in particular, the models didn't exist. And there's a real difference between a lambda calculus with one little extra construct that looks a little bit like system software and what system software actually does and uses and relies on. The second thing that was missing, that's really at the center of this workshop, is a sort of know-how of how do you even deal with specifications that are this large. And finally, the tools were not really up to the task. If you took a theorem prover at the time and you fed it something like, I don't know, the ARM instruction set architecture, like Alistair and Alistair talked about, they would just barf and die. Luckily, time passed, and there was lots of work on these models, and there's too many people to list. This is only a 30-minute talk. I would need at least a 45-minute talk to list those people. And there's lots of things, but I'll mention sort of some key points. So one of them is the work on, there we go, work on TCP that sort of worked as a very close to Peter's heart, and that sort of worked as a warm-up to knowing how to work with these very large specifications. And then sort of more directly relevant to this work, there's been lots of work on user-land concurrency in common architecture, so starting from x86 and then going bigger with Power and ARM. And this is still user-land, so you can't verify any system software. And then more recently, there's a line of work on trying to talk about these systems programming features. And this has been in parallel with also lots of work, again, by Alistair, and others, about the whole, how do you deal with an instruction set that is absolutely gigantic? And all of this has sort of led to a much better know-how and a basis that we can try to start building on. And then concurrently, the tools improve. So theorem provers don't barf so violently anymore when you feed them these definitions. And also things like development of separation logic, not it's sort of necessary. I think all of this could be done in event B if you were particularly keen, but it's made it more palatable in a sense. And for the details of this, this is a twin talk with Ben Simner's talk, who will be later, tomorrow? Something, in the future. So then we can resume our history lesson and go back to Peter Sewell in 2019, who goes, well, by now, programming language theory should be mature enough. So let's try to verify hypervisor, because hypervisors are cool, again. And let's try to be a little bit ambitious. So we'll try to verify a production industry hypervisor. So this is a thing that people in the industry wrote. We don't write it, we don't tweak it, we take what they do, which is according to their state of the art, and we try to make our theory and our tools match. And we want to verify it not against some sort of idealized thing, but against the architectural specification. And this means we want to verify the binary, not the C, because the binary in the end is what runs. And this means looking at the full ARM-A ISA and the concurrency, and in particular, all the system semantics that I mentioned. So instruction fetching, exceptions, virtual memory, all the dirty things. And so in this talk, what I'll focus on is two lines of work that are very much around the idea of big specification, but no verification. So there's a moment where you go, ah. But the idea here is to sort of take the marriage of specification and testing and try to get something that gives us sort of rapid feedback. When Benjamin this morning talked about these response curves, normally verification has a very slow response curve where nothing happens for a while. What we try to do is get fast feedback, that we write the specification and we learn things as we do it. And then we would have to do that anyway on the way to then proving the specification, so it's not wasted work. So there's two lines of work. One of them is on an executable specification of the hypercalls, and another one is sort of, in a sense, a side condition of that, which is that if you want to manipulate the virtual memory caches in your machine, then you need to be careful, and so we want to check that. And then Kayvan will take the relay and talk about the first part.
Okay, so I'm going to give you a quick overview of the architecture of the hypervisor that we're aiming at verifying, and I'm going to give you a reminder for the people who weren't here last week about how the ARM v8a architecture gives different levels of execution privilege for various parts of software. So similar to rings in other architecture, a core can run. Yep.
I was just wondering why KVM? Is it like a standard hypervisor? Is it specific for a specific purpose? Is it used in practice?
Yeah, I'm going to tell. So this is used in practice in Android phones right now, recent Android phones, mostly Pixels.
So about half of the people in this room have it in their pocket right now.
I've had it running for 2 years now.
And it's new and it's clean and the code base is kind of nice once you get used to C. But it really is. It's really very carefully written.
Yeah, we're going to see a bit of actual code later. So in ARM CPUs, you have several exception levels. Typically, you will have EL0, which is where user code runs and most of the Android operating system runs. It doesn't have it. This is the least privileged exception levels. Under that, you will have at EL1 the Linux kernel, and then under that you will have the hypervisor, which is the thing we want to verify. And in parallel to that, thanks to the hypervisor, we can have other operating system or other virtual machines that will have access to these less privileged exception levels. So as Jean said, the aim of the project is to verify the actual assembly of the compilation of PKVM on top of a real model of the ARM architecture. So like a scheme view of the final theorem of correctness that we aim at is to say that basically when a VM is running, in the real view, you have the VM running under the whole architecture, which includes a model of the EL2 exception level. But thanks to the correctness of PKVM, if you were to remove that part of the model and instead replace it with just an interface which corresponds to the hypercalls, the way the VM talk with the hypervisor, then the actual arbitrary assembly code of VM can't tell the difference. So let's have a look at the actual what the hypervisor actually does. It's not really a traditional hypervisor in the sense that it doesn't take full control of the machine. It doesn't do scheduling, for example. All it does is separate, like enforce an isolation of the memory of the host, which is Linux, which is in control of the scheduling, and of the guest, the virtual machines. So it's really just keeping track of ownership of physical pages and allowing through hypercalls for hosts to give some pages to some guests and the other way around. So it's achieving that by using at EL2 a second stage of virtual memory and managing page tables for Linux and virtual machines and allowing these clients to share pages or just give full ownership of pages. There are all other aspects which have to do with allowing virtual machines to have access to device, but we are going to ignore that for now. And this is actually running, as I said, on Android since Android 13 or 14. So let's have a look at the interface. It's quite simple. All these are the hypercalls which are exposed by the hypervisor. So this is what the host, the Linux virtual machine, can ask the hypervisor to do. So it can ask the hypervisor to start a new virtual machine, a new guest. It can ask it to tear it down, and it can do the scheduling by actually loading a vCPU of a particular virtual machine into a physical core and ask it to start running it. And it will get control back using the normal timer infrastructure of Linux. And it can do the isolation mechanism management by explicitly sharing a page from the host to PKVMs, so that later through other hypercall, PKVM can then use this newfound ownership to then give these pages to a guest, or to use it to be able to allocate structures that are used to keep track of virtual machines. So on the other ends, guests also have access to hypercalls, which are mostly, well, they're very simple. They're just two hypercalls which allow the guest to share back pages to the host so that they can typically use that as a shared memory communication channel. So the code of PKVM is quite small. It's around 10,000 lines of C. And interestingly, it's really mostly written in C. Like, they only use assembly for the part which cannot be expressed in terms of the C abstract machine, which is typically going to be the part that mutates the actual state of the hardware. So this will be like changing the page table and enabling the MMU, managing the caches, and doing the TLB maintenance, which is really good for us because it's easier to read C than assembly. So let's have a look at the concrete code, which is massively inlined and simplified of an actual hypercall. So the host share heap hypercall is a hypercall where the host says, here is a page frame number for a physical page. I want to give you, the hypervisor, ownership for that page. So what the code does, it's going to create a little structure which is going to describe who is giving ownership, who is receiving ownership, what check needs to be done, and then it's actually running, like passing this structure, the PKVM memshare structure, into a do-share function, which is actually going to run first the checks, and then if these checks succeed, actually do the sharing. And interestingly, their code is very generic. This same do-share function is used by all other hypercall that may have different initiator and different recipient for that sharing. So let's go inside that function. Again, this is like massively inlined, and we got rid of all the non-interesting aspects, but the two core things that this function does is first update the page table of Linux to remove ownership, well, to mark that this page has been shared, and to update the page table of the hypervisor to now add the information that this page is now borrowed by a PKVM and therefore mapped in the page table so that PKVM can start using it. So how are these two functions actually implemented? They're implemented with a page worker. So in the ARM v8 architecture, page tables are actually stored in memory, and they're structured as a tree so that you can have a different size of mapping, not just page level, but you can have larger blocks, and this will be higher up in a tree. So to update a page table, the Linux code has a very generic page worker which basically implements a visitor pattern over these trees. And whenever you want to do something with these trees, you just write a callback function and a description of where in this tree you want this callback to be called. And you just feed it to that generic structure, which is the worker. And this code is not specific to PKVM. It's also used for the normal implementation of KVM in Linux. This is like actual instance of the visitor where you will go down the structure of the tree, and depending on whether you have a leaf of the tree, you will call the callback function with information of the context, or so this will be the leaf context, or a higher part of the tree, and you give it a different context.
Do you update the Linux code?
We or the PKVM developers?
I understand that your system is changing entries and tables. Does it just reach right into the, I mean, do you freeze Linux somehow and reach in and change the page tables, or how is this?
So the hypervisor is managing the second stage of virtual memory for the Linux mapping, and it's if the KVM code is unmapping a page from Linux, it's because Linux has, through some hypercall, told the hypervisor that it was fine to do it. So if Linux did something wrong, it's going to get frozen by the execution of that hypercall.
I see. So literally this code replaces a piece of Linux.
It replaces the normal implementation of KVM which runs at the same execution level as Linux, because usually Linux runs itself at EL2. And this new implementation of KVM pushes Linux down to EL1, and the stage 2, the management of the stage 2 page table of Linux is the thing that remains at EL2. So it had to introduce also new hypercalls for the creations of guests, because these were usually just doable right away by Linux, because now it's separated. But if Linux calls the hypercalls wrong, it can get frozen.
Have you thought of this? I mean, this is a different question, but here this page table walk code is available to the user, but let's say in x86 architecture where it's built into you know, the, if you will, microcode or the processing of the machine, would you be able to do anything like this?
So there's two things, right? So maybe it's worth sort of drawing the big picture. So Linux maintains page tables, both for itself, so that it can access memory, and for the sort of userland programs that are running, right? What PKVM does is it adds another layer of that. So whenever you have an access, there's a level of translation sort of underneath the operating system. And so what this is changing is these sort of lower level tables. So these affect the translation of Linux and of the other virtual machines. So it's not replacing really, it's really having a copy of virtual memory but underneath virtual memory, if that makes sense. The way it's implemented, however, is by kind of hijacking the code of Linux, but this is kind of an implementation detail.
Right, these page walkers are really only used for the stage 2, even in the non-PKVM version of KVM. In Linux for ARM64, you have two implementations of page walker. The normal stage 1 page maintenance code for both Linux and EL0 codes is not this one. It's a completely different implementation.
And maybe I want to clarify another thing you said, Warren, before I take David's question, which is this is the code inside the hypervisor that is manipulating the page tables. This is completely different from the walker inside the memory management unit that is also concurrently reading these page tables. Right? So it's not replacing the MMU. It's manipulating it.
Sorry, did you have the same level of privilege? In the sense, like if this manager of the page table has a bug, you get the same compromise that you will get like in the back on the Linux page table manager?
Yes, this code will be running at EL2.
Yeah, so this is a big hole. So they run at the two managers run at the same privilege, no?
No. So Linux is way less privileged than PKVM. So if Linux shoots itself in the foot, then it's bad for Linux, but it's not bad for the other virtual machines.
For the first stage of virtual memory of Linux, which is this code is running at EL1, so it can only break that part. And at the second stage of virtual memory, which is managed by PKVM, cannot be accessed by Linux. So Linux cannot affect the page table of guest, and it cannot affect its own second stage page table.
But
David,
does the TLB, I mean, do you insert these entries into the TLB and mark when?
No. The machine does that concurrently.
I see.
Right.
We make them visible to the TLB, or to the MMU.
But you have to mark that when you set that page that it has an extra restriction or something. You're changing the TLB entries from what they would be normally. Is that right or not?
I guess you're indirectly affecting the TLB entries by making things visible to the MMU that it can then choose to fill the TLB with. You're making faces, David.
Well, so I didn't really have a question. It was more just an observation that we seem to have an actual experiment going on here in the difficulties of specification and the social aspects, because you're talking past each other.
Yes.
This is absolutely bog standard hardware walk page table. ARM is no different to x86.
Okay.
They are just walking through the page table structure in memory in order to modify it as you normally would in the OS. And they're doing the stage 2 translations because they're doing a VM. That's it. They're not doing anything special. They're not fiddling with the TLB. Just absolutely standard page table.
Okay, so they're just managing the page table.
Yeah, this
Yeah,
is just
simply
a software
modifying the page
managing the page table. The actual translation for actual access is still in hardware. Okay, I'm going to skip a bit. So now, this was the code. Now we're going to show you how we do top-level specification of these hypercalls directly in C so that we can actually run it. So the idea is that the real code of PKVM has some state, the state of its C program, and you have these page tables which are trees stored in the memory. But logically, these page tables are really just partial maps from virtual addresses to physical addresses plus some permission for these addresses. So you could, if you were to write it in a more functional programming language, you would just really have these partial maps. So what we do is we make a ghost copy of the interesting part of the state of the C program in a style which is much more abstract. So instead of having precise trees, we really have these partial maps, which could be modeled by more than one tree, depending on which granularity you want to do the actual mapping. And we are going to recreate this state whenever a hypercall starts executing. So this becomes like the pre-state of the hypercall, and we're going to record it at just before the hypercall exits back from EL2 to the execution of Linux. So this gives us the post-state of PKVM after having executed the hypercall. Once we have that, we can just do a diff between these two recordings to just actually see what changes have been made to the state of PKVM by the execution of the hypercall. But we can also write what we think should be the spec of that hypercall by writing a function that takes as input a ghost state, which is going to be the recorded pre, and then produces the post state that we think should be the one that we will record once we exit the hypercall. And then we can compare the one we've computed using that function and the post state that we have actually recorded. And if they disagree, then the code of the hypercall is not correct with respect to the spec we've made. So this is a simple picture, but in reality, things are a bit more complicated because the way the code of PKM is written, you can't really have at any point ownership of the whole state of PKVM. You have subcomponents which are owned by specific logs, and typically the code of PKVM will not take all of these logs at the same time. So we could insert just a big log whenever we want to do the recording, but we would be reducing the non-determinism of the actual code. So we would be changing the behavior. So what we actually do is we record the pre-state progressively as logs are being taken, and then record the post-state as logs are being released. So we are, during the execution of the hypercall, progressively like accumulating the ghost state. Okay, so once we have that, we can write that function, which we are going to write in C so that we can actually run it alongside the code of PKVM. But this is still morally a pure function. It's not changing the state of PKVM. It's only taking a pointer to a structure which represents the ghost state, and it's going to purely in C, so not really purely, but it's creating a new ghost state, but in a separate part of the C state of the PKVM executable. And it's written in a, except for the syntax, you could really write that in OCaml. It's really, there is an implementation in C running at EL2 of partial map, and then all it does is looking up with a key, adding a new singleton in the map, removing a singleton, and doing explicit checks on values of registers by inspecting that ghost state. So once we have that, because it's written in C within the code of PKVM, we can just run it. And then we can, with a bit of hacking, get colorful divs, which will actually show you, as you run hypercalls, a graphical representation of what the hypercall has actually done. For example, this must be host share heap. At the top, it's telling you that after you've run host share heap, a new mapping has been added to the shared view of the stage 2 mapping of the host, which now mark that a particular page has been shared. And then in the page table of the hypervisor, we now have an actual mapping of that page. So you will see that this is referring to the same physical page, but physical address, but they have slightly different virtual addresses because the host and Kayvan have different mappings. And then also some registers have been updated, like all the information in the Go state that we have recorded will be shown, they will appear in the diff if they have actually changed. Okay, so the idea of doing this is that, as Jean said, like when we do traditional verification, we would need to first make up a model, and then this will take quite a bit of time because we are not the people who wrote the hypervisor. So we need to reverse engineering what is the intent of the the implementation of the hypercalls, and we wouldn't be able to actually run it right away. Whereas if we do it directly into the code and add this recording infrastructure, we can, using these diffs which get generated by the execution, try to infer what should be the spec and then progressively do it. And this, in turn, because it forces us to read the code, allowed us to find bugs just by trying to infer what the spec should be. So now Jean is going to mention another aspect of our study of Pichon.
So this work looked at the pre and the post state of a hypercall. But in practice, if you read the code of the arm, it tells you this is not enough. It's not enough to have a good pre and a good post. Also, the steps you take in between should follow a very specific discipline. Otherwise, it voids all the isolation guarantees. Typically, the way this looks is that, you have a sort of sequence to follow of enough barriers, enough invalidation of the TSB, of the TLB, and enough barriers after that. So you would think naively, it's easy, I just look for this pattern, and it will be fine. The problem is the real code doesn't look anything like that, because in practice it tries to bunch the barriers and the cache clearing. And so what you have to do is look at the actual architectural specification of, when is there enough ordering between these accesses that the MMU cares about. The problem is the specification is super big, and it's got pretty subtle behavior that stems from the fact that there isn't a single state. So you don't want to reason with respect to the specification. It's just too horrible. So instead, what we want to do is try to have a small specification, and the idea is to identify conditions under which this single state that I said doesn't exist, sort of exists enough. And then we can make a nice specification that sort of relies on this simple state and then checks that the conditions are met. And then the way this looks is basically some little automata that make sure that you sort of push things around in, towards the right direction. So when you edit the page tables, you do enough of the things that in the end, the state remains good. And then we can implement this similarly to what Kayvan described as an online checker, again, in the code of PKVM, by having ghost state that reifies the automaton state and then ghost transitions that push these around. And in doing so, we found a bug. And this is our model running, and then the very bright red at the bottom means, oh, you did something very, very wrong. You were supposed to have a DSB here, and you did not have a DSB. Therefore, your code is wrong, all the isolation guarantees do not hold, and this was a real bug in PKVM that we found before they shipped it on your phone. So that's a pretty good win. So to conclude, I think this idea of executable specification is great because it allows you to specify and test at the same time. So you get, twice as much value. It's pragmatic because it works. There's really a great synergy from looking at the code and this is fishy. And anyway, it's a thing you would have to do on your way to verification. And so there's really this idea that you can do big specifications. PKVM is small, but it's still a real piece of code that interacts with all of the ARM architecture, and you can do that using just C. And C is an amazing specification language. It's also awful at the same time because it doesn't have algebraic data types, but it's so easy to use. There's zero cost to adoption in the code base, right? It's already there. And it has fantastic tooling. You know, you can like jump through your specification using VS Code and jump back to the piece of the hypervisor that it refers to. It's all completely seamless. We have no verification tool that is anywhere near C in terms of user experience.
C++.
No.
Yes, it's the, well, no, it's not. Virtual dispatch is a bitch. And it's immediate tech transfer, right? Because it's C. So program, you can just show this to a programmer. You just need to do it to make sure that they're actually happy. But in theory, it's totally doable and maintainable by C programmer, not tomorrow, not in 10 years, but today. So you should try it in your code base. Thank you. Mistake for lunch, Philippa has asked me to make some propaganda. So I will be taking questions after that.
Yeah, so Matthew?
I just wanted to know, you said it's zero cost to adoption, so have they adopted it?
No, because as I said, we haven't showed it to them quite yet. But it's zero cost to get started, I think. Because if you want to start doing that, then you just start adding things to your C code. You don't need to write binders to work with whatever OCaml extracted from Calc. It's just like, it's here, it's now, and you get exactly the value that you put the effort for in.
Right, the two things we didn't need to do was re-express the interface so that we could look up the state of PKVM into some other language, and we didn't need to port a language to be able to run with a one-page big stack without MMU, without allocator, without standard library, without anything. Just like add more code.
All right, so let's take the rest of the discussion over lunch and thank the speakers again.